Hi everyone! This is a series about the OpenVINO DL Workbench, which is a web application that allows you to easily profile your model on various Intel hardware architectures. In this video, you will learn how to calibrate a model so that it can be executed in a more effective way using a lower precision. So usually models are trained in floating point 32 values, and we can produce a calibrated model that would bring some accuracy drop, but at the same time, the speed up would be really considerable. To create a calibrated model, you firstly need to import a model following the traditional path from the configurations page. So here's the import model page. In the previous video, we've covered how to import a model from the local file system and then proceed to the inference experiments. In this video, we'll use another way. We'll import a model from the Intel Open Model Zoo. It exposes a lot of public and Intel models for various tasks such as classification and object detection. Here in the list, you can see models from different frameworks like Caffe, Caffe2, TensorFlow, MXNet, PyTorch, and so on. Let's use the SSD MobileNet V1 Cocoa model from TensorFlow. If we expand the row, we will see the corresponding paper and the license. Now let's select the model and click Import. Compared to the import of a local model, here you do not have to provide any additional data, and the recommended precision is automatically selected for you. So we click Convert and wait for a while because the model is being downloaded from GitHub or Google Drive depending on where this model is located. Once the model is imported, you can see that the type is already set, unlike when you import your model from the local file system. So it is SSD, and we can also see the precision of the model and so on. So we can select it and proceed to the inference on the CPU device. Once the inference on the CPU device finishes, we can proceed to the calibration logic. In order to perform and configure optimization of your model, go to the Optimize tab. We see two methods here, the INT8 method and Vinograd. But Vinograd is only available on machines with the AVX 512 instruction set. The current workstation doesn't have such a set, so you can only optimize your model with INT8. To read more about the method, refer to the official documentation or see some snippets of the optimization tips on the right. So you select the INT8 algorithm and click Optimize. Here, you can firstly provide a subset of images in case you do not want to calibrate on the whole dataset. Usually, and it is mentioned here in the tips, it is better to use at least 3–5% of a calibration dataset. The bigger the dataset, the more accurate the resulting model. So once you have selected the proper subset, you must choose an optimization method. Currently, two methods are available: the default method and the accuracy-aware one. Accuracy-aware is an optimization method with the controllable drop of model accuracy. It allows you to boost the performance of your model by keeping the accuracy at a specified level. Specify the maximum accuracy drop here. The delta between the accuracy of an original and the calibrated model is guaranteed not to be greater than the delta specified here, so 0.5% in our case. Please pay attention to the new optimization method that appeared in the 2020.1 release. This method is called default, and it allows you to significantly increase the model speed by keeping accuracy at an appropriate level. However, the accuracy of the resultant model is not guaranteed to fall within the specified threshold. So this is a trade-off. You either calibrate your model to be as accurate as possible while the accuracy of the resultant model is defined by the algorithm, or you select the method and specify the maximum accuracy drop, while not the whole model is executed in the INT8 format, so possibly you're not getting the maximum performance increase. So we'll use this optimization method. Let's click Optimize. It will create a child row in the configurations table representing an INT8 version of the original FP32 FP16 model. In our case, it is mainly the FP16 model with the FP32 inputs, so we have one nested row, and the more optimizations you run, the more rows you get. You can play around with the subset size, and you can play with the algorithm and figure out which combination allows the best performance of your model. Once the optimization finishes, the basic inference with the default settings, which are one stream, one batch, is taking place, so you can immediately compare the calibrated and the original versions of a model. Also, the calibration time heavily depends on the size of the dataset and the model, so a bigger dataset results in a longer calibration process. So let's explore it. Here we can see a new precision of the model, INT8. Several layers are still executed in the FP16 format, but the most important thing here is the latency value. Even with the default settings, the latency has decreased, but the throughput has increased dramatically. Okay, before we compare the performance of the models, let's firstly check their accuracy. Let's begin with the original FP16 model, and then we check the accuracy of the calibrated model. So, as you can see, the accuracy of the INT8 calibrated model is lower than the accuracy of the original model. It is nearly a 3% drop. So we can check that there was the default or performance calibration algorithm. That means we could not specify the accuracy drop. At the same time, the algorithm provided the best performance of the model. We can click the row and explore the single point that we have here with the distribution of the layer time within the whole execution. Here, we can see that a new type of layer appeared, which is this quantized layer, which refers to calibration. Below, we see the table with statistics of how each layer was executed. So we see a lot of reorder layers, const layers, and so on. Now we can compare the performance between the INT8 version and the original version of the model. So we can go to the compare page and select both projects. So let's select the points on both graphs. We see that the latency differs between the runs and that new layer types appeared in the calibrated model. Also note that these layers are from the executed graph. They are not from the intermediate representation, but from a particular device, and in our case it is CPU. And now in the per layer table, we see that the model executed on a CPU was slower than the INT8 model. We can view all the layers where the difference took place. At the same time, there are layers that are faster in the original model, and that brings you to the question of what delta time you consider negligible and what delta time threshold determines which layers are faster or slower. So we can explore any layer that, for instance, did not exist in the original model. And you can see that a lot of reorder and const layers appeared in the INT8 model. So that's it to creating a calibrated model, comparing it to the original version, and measuring accuracy. Thanks for watching. See you in the next episode.